Today we're going to be talking about error. But before we start talking about error, I want to help you understand why we care about understanding error associated with a measurement. Any scientific measurement has some associated error, and characterizing this error is so important to understanding whether this data is reliable. If we make a measurement in the lab and we don't understand the error associated with that measurement, it's not a useful or helpful measurement. We need to be able to understand how accurately we know a measurement to be able to know if that measurement is truly valid. So we're going to be spending the first few lectures talking about statistics related to chemistry, because statistics allow us to characterize this error. So the example that I have of this picture is measuring glucose concentrations in blood samples. So if you're a person that has diabetes, then you know that understanding the amount of glucose in your blood on a daily basis is very important so that you can calculate the proper amount of insulin that you need for a particular day. If you just blindly take a measurement and don't understand the error associated with that measurement, it doesn't mean anything. You need to be able to know, okay, is this measurement that I'm taking actually accurate? Is it close to the value that is really in my blood? How do I know that? So these are some of the things that we're going to be talking about in this class. How we can characterize this error associated with a scientific measurement. The topics that we're going to be talking about is why this error is important, what are the types of error that you'll typically see in the laboratory, and those were typically made up of systematic and random, but we'll talk about one more. We're also going to introduce some terms such as average and mean, and precision and accuracy. There are three main types of error, really two main ones and a minor one. There's systematic error. Systematic error arises because you have some flaw in your equipment or the experiment isn't designed properly, and we'll give some examples, but the key part about systematic error is that it's unidirectional and that it's reproducible. It's very reproducible. Random error or indeterminate error arises from some uncontrolled variable in a measurement. Random error has an equal chance of being positive or negative, and the big key here is that it's always present. It can be minimized, but it can never be completely eliminated. You can also have things like gross error, which we all do. So gross error is more talking about a big mistake like dropping your sample on the ground or just completely destroying your sample apparatus. That's error that also occurs, but the two main types of error that we're going to be focusing on are systematic and random error. So even if you're being very careful and conscious in the lab, there are still two main sources of error. So systematic error is very common. It's something that I come across all of the time as a chemist. One example might be if you have a pipette. So say you're using a micropipette and you believe that it's delivering 1 ml consistently. But maybe you get some hint that it doesn't look like it's quite delivering 1 ml. Well, maybe it looks like it's delivering less than that. You want to check that or correct it. So I want you to think for a second about how you could check this or correct it. All right, and the way that you could do that is you could try delivering water, trying to deliver 1 ml of water and weigh that out. We know the density of water, 1 gram per 1 milliliter for water, which is the density. So 1 ml should weigh 1 gram. So if you weighed out your 1 ml, and if it wasn't 1 gram, then you would know that your pipette indeed wasn't calibrated correctly. So you would have to get your pipette recalibrated, or just keep note that you're only delivering 0.98 rather than 1 ml. Another example is if you had a pH meter standardized incorrectly. So typically when you use a pH meter, you have to calibrate the pH meter with buffer solutions, and we'll talk about what a buffer means later. But a buffer solution is something that just stays at a specific pH. So let's say that you thought you were calibrating it at pH 7, but the buffer actually had a pH of 7.08. So now this is going to consistently give you a pH reading that's lower than the actual value. And that's a problem. So I want you to think about, how can this be checked or corrected? The way that you would check this particular situation would be with some really trusted standard buffer solutions. Again, we talked about these standard samples a few minutes ago. So standard samples are samples that typically have been measured by several different methods, and they're highly confident that the value is close to that quote-unquote true value. So we would use a standard solution, a new standard solution, to check it. And if it wasn't calibrated correctly, then we might get several different buffer standard solutions, one at 4, one at 7, one at 10, to then recalibrate that pH meter. So systematic error can be evaluated with standard samples, and it can often be corrected with proper calibration. So systematic error, again, we can usually remove a lot of systematic error. We can also have random error. So two examples are electric noise in the circuit of an electrical instrument that's giving you noise in your spectrum that you're collecting on a spectrometer, or you could have error associated with an experimental reading such as temperature on a thermometer. So we can also think about how we could minimize these. So with random error, we can't ever completely remove all of the random error, but we can think about minimizing them. So for this electrical instrument, some of the noise in electrical instruments has to do with environment, whether it's maybe your spectrometer isn't in the most stable situation. Maybe it's in a situation where there's a lot of ground vibrations or temperature fluctuations. One way that you could minimize the electrical noise is getting this spectrometer into a more stable situation. For the thermometer reading, so if we were to read the temperature on a particular thermometer, there'd be some error associated with this reading simply because we don't have a ton of significant digits. Say we're reading this temperature in Celsius. On this scale, we would say, okay, it's a little bit more than 34, but less than 36, so maybe we'd say it's 35. So we'd say it's roughly 35 degrees Celsius, but there's some uncertainty. It's not exactly 35. It may be, but that's as certain as we could label that temperature. If we had a more precise thermometer, for example, now there's a tick mark for every single degree here. Okay, so now it's above 36, but not quite to 37, so maybe we might say that this is 36.9 degrees Celsius. So the more precise your thermometer, so some of random error can be reduced by using better tools, essentially. So these are just two different examples of how to minimize random error. So you can never completely remove random error, but it can be minimized. Steps can be taken to minimize random noise. So again, when we have a set of measurements, we have to make this call about what's the best value. So if you have individual results in a set of measurements, they're seldom identical. So what's typically accepted in all fields of science is, if you're fairly confident that there's nothing wrong with any of those measurements, then you simply just take an average or mean of those set of measurements to get the best value. And all an average is, you're probably all familiar with this, it's just the sum of your individual results divided by the total number of trials to get your average value, which in this class we're typically going to label as X bar. Next, we're going to introduce this concept of precision versus accuracy. So precision describes the reproducibility of a result. So if you measure a quantity several times and the values agree closely with one another, then your measurement is precise. So here we have some target practice. All of these arrows hit the target really close to in the same spot. So player playing darts is a very precise player. Accuracy describes how close your measured value is to the true value. So if a known standard is available, accuracy is how close your value is to the known value. So using our analogy of someone playing darts on a dartboard, you could say someone had decent accuracy if they were all really close to this target. So you can have precision and accuracy, or you could just have one or the other, or neither. If you have purely precision but not very much accuracy, then this is primarily systematic error. So we've got a whole bunch of darts that are in the same spot, but they're still pretty far away from the center of our target, or the true value. So this is systematic error. Here, our average value is going to be pretty close to the true value, but we don't have a whole lot of precision. So this is accurate, but not precise. So if you have purely accuracy, then you're just probably going to have some degree of random error and not very much systematic error. You can, of course, have good precision and accuracy, which is the gold standard. Lastly, we're going to talk about absolute error. Absolute error is simply the difference between the experimentally determined value and the accepted or the true value. The reason why we put the true value in quotations is because there's no perfect way to know exactly what this true value is. We can only kind of do a lot of measurements with several different methods to get close to what the true value is, but we can never know for certainty what this true value is. So in the next couple lectures, we're going to be talking more about how we can define what our error is, what our uncertainty is. We're going to introduce the concept of uncertainty into our next couple lectures. But the key take home here is that it's so important to understand the statistics associated with scientific measurements, because they help us understand the validity of that scientific measurement.